Hello, everyone. Welcome to the AI Journal seminar series. My name is Tom Shi. I am professor of aeronautics and astronautics at Purdue University and the editor-in-chief of the AIA Journal. And thank you for joining us. The AI Journal seminar series was established to thank our authors, our readers, our reviewers, our editors. It has two tracks, keynotes and author seminars. The author seminars involve talks linked to articles published in the AI Journal during the past 5 years. And the goal there is to connect the authors and readers to further expand on the significance of the research. The keynotes involve talks on emerging and potentially disruptive topics, including those that still vex us, such as turbulence and structures. Now, these talks are given by leaders in the field. And the goal of the keynotes is to inspire and nurture research that still needs to be done and published in the AI Journal. Today, we are delighted to have Professor Wenbin Yu of Purdue University give today's keynote. Before introducing Wenbin, I want to thank the AIA Journal Seminar Series Committee, chaired by Professor Paul Tucker of the University of Cambridge, and co-chaired by Professor Earl Dow of Duke University for organizing and planning the talks in our seminar series. I also want to thank AIAA, the American Institute of Aeronautics and Astronautics, and the AIAA Publications Committee for the support, and Cassini in providing this platform. For Wenbin's keynote, I originally invited Professor Byron Pipes to host. However, Byron couldn't make it at the last minute, but we're delighted to have Dr. Jonathan Goodsell to introduce Wenbin and moderate his Q&A. Jonathan is the Deputy Director of Purdue University's Composite Manufacturing and Simulation Center, a center where Byron Pipes serves as the director and Wenbin Yu serves as the Associate Director. Jonathan, thank you for joining us, and please help us introduce Wenbin.
Thank you very much, Tom, and I'm pleased to get to be with you and introduce my good friend and colleague, Professor Wenbin Yu. He's the Milton Closser Professor in the School of Aeronautics and Astronautics here at Purdue University. And he came here from Utah State University, where he worked for a decade after receiving his doctorate in aerospace engineering from Georgia Tech in 2002. He's also the Chief Technology Officer of AnallySwift, and he's the Director of the Composites Design and Manufacturing Hub, positions I've worked with closely with him over the last over 10 years. We work closely together, and it's my pleasure to introduce him to you as he'll discuss shifting the paradigm of aerospace structural modeling with AI. So Professor Yu, and I guess I'll ask everyone, put your questions in the chat box as we go along, and I'll moderate those when the time comes to the end of the talk.
Thank you, Jonathan, for the introduction. And I really appreciate the AIA, particular Tom, to setting up this wonderful platform for me to have the opportunity to interface and also share with the global aerospace community, particularly the aerospace structures and materials community. And before my talk, I also want to acknowledge the contribution from my students and my postdocs and research engineers, including current and former group members. And in the past over 2 decades of research, and most of their work has been reflected in this talk. And I particularly want to acknowledge the contribution from Dr. Xin Liu, a professor at UT Arlington right now. It was about maybe 9 years ago. It was him who pushed me into the exciting field of AI and machine learning. And I still remember, one day he came to my office and said, Professor Yu, the mechanics stuff is pretty boring. I want to do machine learning. At those days, AI is not as popular as machine learning. We call it machine learning. Then I challenged him to thinking carefully and seriously and critically about the problems we really need AI to help with. So the answers to those challenges I posed to him basically laid the foundation of the remaining 10 years of work till now. Some of those are related, particularly in the AI and ML part of the talk. So in this talk, I'm going to share my personal perspective of aerospace structure modeling, particularly how our field should be, reacted or shaped by the artificial intelligence and machine learning, and also what is the relationship to the physics-based modeling. I hope that my talk can add some clarity to the maybe already too many discussions about AI. And so I don't want to add noise to already pretty noisy discussions, but I want to add clarity to the discussion and also possibly inspire some new thinking about aerospace structure modeling in the age of AI. The first that I want to show this that I think many of you know last October, the Nobel Prize in Physics also was awarded to two researchers for their foundational discoveries and inventions that enable machine learning with artificial neural networks, which is the very technology that modern AI is built upon. So today, AI, we know it's rapidly transforming many aspects of our life. So the AI researchers get recognized at the highest level is not surprising. But what is surprising or remarkable is that this recognition comes from the physics community itself. So it really poses the question, at least to me, when I saw it last year about this time. And this news, I say, does this suggest that the most impactful or the best research in physics today now is artificial intelligence? Should we still devote ourselves to study thermodynamics, solid mechanics, finite element methods, aerodynamics, all those physics-oriented courses, or should we, as professors, should teach or not? And is physics-based modeling still needed or even relevant? Those are the questions I was asking and also basically motivated by this news. My personal opinion is that I believe physics-based modeling is still needed. It's not just to justify my job, but I will use a very well-known scientific history to prove my point. So I'm showing three scientific figures on the screen, and pretty indicate in your chat box that one or two or three for the person you can recognize. If you can recognize all of them, you type 1, 2, and 3. If you cannot recognize any of them, you just type 0. So I gave you a few seconds to do that, and I have the numbers on the top of the pictures. And so if you can recognize all of them, just type 1, 2, or 3. If you cannot recognize any of them, you can type 0. And the first person, and let me give you the answers. The first person is Tycho Brahe, who carefully and spend a lot of time and effort connect a vast amount of astronomical and planetary data. And the second person is Kepler, who used Brahe's data and derived several formulas, which are very famous. I think we all learned that from the physics in middle school and high school, depends on where you get training. And those formulas still bear his name, but he's a genius. But his work is mainly what I call as curve fitting, to discover patterns, use formulas to describe the patterns. And the third person, which is Newton, I believe all of you can recognize him. They took things much further, not merely just describe the patterns, but uncovering the fundamental physics behind them. And his work, to me, is the essence of the physics-based modeling, because his model not only applies to the moons and stars, but also applies to cars, airplanes, and human body movements, and even the foundation of material science engineering, the molecular dynamics simulation, also is an application of Newton's law. So I believe in the age of AI, our role as a physics-based researcher is to create Newton-like models. Those models are explainable and also extrapolatable, and also predictive, not only for the data we have seen, observed, also out of the domain we have seen, we have observed. And those models, if we can find these models, those are the most accurate and robust, and also most efficient solution one could have. It would be much better than data, than whatever fitted surrogate models based on the data. And also, this kind of models can provide the high quality training data for AI to make AI more intelligent. And also, if we can implement these models in a robust computational tool, these computational tools can be used by AI to deliver answers. So that's my argument for why the physics-based modeling is still needed. For nearly 3 decades, I have focused on developing efficient yet accurate physics-based models to connect the microstructure features like fiber and matrix and microstructure topology to the microscopic behavior of the system. And usually, particularly these days, because of the advance of the manufacturing techniques and also advance in the material science technology, our aerospace systems are increasingly made of anisotropic and heterogeneous materials like composites and other advanced materials. As designers, as aerospace structure engineers, we are more focused on the performance of systems in the size of meters or dozens of meters. But the performance, if you're dealing with materials like composites, we know they are directly affected by the microstructure features like carbon fiber. They are in the diameter of the microns. And it's impossible for us to directly capture the details of the microstructure, like the fibers, to predict the structure level performance. Some type of modeling is needed to rigorously bridge the different scales and capture all the anisotropy and heterogeneity. And how to do it? And I think that we need to first to exhaust the capability to do it physically, then do the data-driven approach, which is just like using machine learning and AI to do it. So let me to show how conventionally we usually do it. It's conventionally, the conventional approach is what I call the bottom-up approach, with various assumptions for each scale, and then the information passing from the bottom scale or the fine scale to the coarse scale. For example, for a fiber reinforced composite laminate, what we do, we first use the microstructure using micromechanics and to compute the laminar constants in terms of fiber matrix properties and microstructure arrangements. Then we use structure mechanics models to do the prediction of the system level performance in terms of vibration frequency, mode shape, and buckling load and displacement, all this type of stuff, and damage and failure, of course. And besides, if you look at the micromechanics, structure mechanics, which is this domain or contribute to aerospace structure modeling, in each domain, within each scale, we have different assumptions lead to different models. And also there's a when we do the problem this way, there's also a more fundamental assumption called the scale separation assumption. For example, I have a, originally, this is of course is artificial, heterogeneous panel like this. You have fibers matrix. If we do this approach, what we do is basically we place the original heterogeneous panel with 3 homogeneous layers. By doing that, we create artificial discontinuity between the layers. Usually in our analysis, we assume layers are perfectly bounding, so there should not be a discontinuity. What the real discontinuity should happen between fiber and matrix. But this kind of assumption would be okay if the diameter of the fiber much smaller than the structural dimension, like the thickness, for predicting the global response, vibration modes and buckling load and all that. But it will not be okay if you want to predict the space concentrations and space jumps and also the strengths and damage and failure. That's why kind of like the failure of composites still remain as an open research question. And sometimes even for the global behavior, it's not valid. For example, we have a honeycomb sandwich structure. The conventional approach, what we do is that we first take the honeycomb unit cell and homogenize them to be a homogeneous material, then treat it as a multi-layer laminate to do the analysis. This time, the scale separation assumption is not valid because the size of the unit cell for the honeycomb is similar as the thickness of the panel. We have to do it simultaneously. We cannot do it two-step like this. So for this time, you will get a significant difference even for the global responses later along the local stress and strain and damage studies. So I'm not following the conventional approach. Instead, what I have been working on is a top-down approach by focusing on the analysis of the system at the system level of the structure. For example, for engineer system, no matter how complicated they are, like a Boeing 787, when you go to the structure analysis, it's a combination of 3D bodies, 2D plate and shell bodies, and beams, thin-walled beams. We classify this terminology using the external geometry only. So if you have a body, all the three dimensions of similar size, we treat it as 3D body, use 3D elasticity, 3D continuum mechanics to do it. If we have one of the dimensions much smaller than two other dimensions, we analyze as a plate, or if it's curved, then as a shell. If we have two of the dimensions much smaller than third dimension, we treat it as a beam, and idealized as a line. And then, of course, the beam itself can be initially twisted and curved like a helicopter rotor blade. And if all of the three dimensions are order of magnitude different, then you have thin-walled beams. And the structure itself, we only say classified according to external geometry, but the structure itself can be made of advanced materials featuring general anisotropy and heterogeneity at different scales. It could be built up, could be lattice materials and metamaterials and conventional composite materials. And to model these structures, and we first decide which model we want to use to describe the relevant system level behavior at global scale. Then we look at how do we characterize our material, calibrate our material so that the material scale, then you have two model representation. What naturally you need to do is to minimize the loss of information between these two model representations. And this Mechanics of Structure Genome and its companion Wolfgang code is what I invented to achieve this purpose. It has the potential to achieve the best model for all types of microstructures at a given efficiency. And the central to Mechanics of Structure Genome is the concept of structure gene, which is defined as the smallest mathematical building block of the structure. And depending on the dimensionality of your material, and it could be a 1D domain or 2D domain or 3D domain. For example, if you're dealing with a laminate, at the material level, the laminate, they are uniform in plane, so only difference will happen through the thickness. Then you transverse normal line will be a 1DST. And as another example, if you want to do a dynamic simulation of a helicopter rotor blade, what we do is that we take the cross-section and compute the corresponding blade property to treat the entire blade during the aeromechanical rotor analysis, entire blade as a series of beams. And the connection of different cross-sections, of course, form the entire structure genome of the blade. And some of you might be familiar with the concept of RVE, standing for representative volume element. And compared to RVE, ST can mathematically reduce the dimensionality of the problem. Last month, I attended a composite conference in the United Kingdom, and there was a talk for doing some machine learning related surrogate modeling for composite laminates. What they also did is that take a 3D block and carry out a series of RVE analysis, then take this data, did a surrogate modeling to speed up the process. So I basically challenged the presenter, say, hey, for this case, you don't have to take a 3D block. You can take a 1DST, which is transverse normal line, and formulate the physics-based model. I believe it will be much more efficient and also much more robust and predictive than your surrogate model trained based on 3D RVE. And also that some of you may think that in the literature, a lot of people use 3D RVE to provide a prediction for unidirectional fiber reinforced composites. and which again it's unnecessary. And also you will say for stiffened panel, that's if you have stiffener running in one of the directions, that in the literature people take the idea of different stiffeners and also some finite distance lengths along the stiffener direction. Again, those are unnecessary waste of computational cost, because at the material level, if it's unidirectional fiber into composite, then it will be uniform, mathematically and physically uniform along the fiber direction, and also for the stiffness. And unless you artificially create not uniformity, otherwise it should be uniform, and it can be predicted by a 2D domain. And the 2D domain, a 2D-dimensional analysis will be sufficient to perform the constitutive modeling for this type of material or structure without any loss of the fidelity. Mechanics of Structure Genome greatly simplify the reasoning behind the aerospace structure modeling, and we only need to answer 3 basic questions. And given a problem, we ask what is the microscopic model we want, and to capture system level behavior that at the efficient, affordable level. Then you ask question, what is the original model needed to capture the right physics? Then the third question is, what is the fundamental building block of my structure could be adequately represent the constitutive behavior of the structure? And after we have the answers to these 3 questions, we follow a 3-step basic procedure. We express the geometry and kinematics of the original model in terms of the model we want. Then we write out the information of the original model in terms of the kinematic variables of the global model. Then you minimize information loss between these models. You solve for the unknown information here. I call it W, is the fluctuation function in the terminology of micromechanics, and warping function for the structure mechanics. But fundamentally, it's an operator mapping the global model to the original model. And I will use a very simple example. And most of aerospace structure engineers, if they deal with composites, they know this classical lamination theory. And traditionally, what we did to derive this theory is that we first invoke the Kirchhoff assumptions, which is essentially a plane strain assumption. Then we invoke the plane stress assumption. And if you're familiar with 3D elasticity, you know plane strain and plane stress cannot coexist. They are contradictory. If one theory uses both of the assumptions, if the Poisson's ratio are not equal to 0, then they are contradiction to each other. Despite this self-contradiction, we still use that theory. And for composites, that's the most extensively used model in industry. If you use MSE, then you can get rid of all the assumptions. As we say, that you only need to answer 3 questions. What is the original model? Is 3D continuum mechanics with layer-wise heterogeneity? What the model you want? I want a classical plate model, having 3 degrees of freedom for the displacements, have the membrane strengths and curvatures and forces and moments. And then what is my structure gene? Is the transverse material line. I indicated different layout and material. Then the next step, what you need to do is to follow the 3 steps, write out the formulas. And now the global kinematics, variables not only have the displacement, you also have the rotations, not only have the strengths, you also have curvatures. And after you minimize loss of information, you solve for the roots of the, whatever the connection between the original model and the microscopic model. And after that, you get a result, which is still in the form of the classical plate model, but you didn't rely on any of the ad hoc assumptions, plane space assumptions, or Kirchhoff assumptions. And you get the complete space strain displacement 3-dimensional fields. And I have equations listed here, but I only want to highlight the points that there are some terms recaptured by this process without inductive assumptions. And another benefit of using mechanics of structure genome that it's not only applicable to composite laminates, it's also applicable to stiffened panels, to sandwich panels, to perforated panels. And the only difference, the derivation process will be the same, but the only difference will be the ST will be different, which is the fundamental building block of the panel will be different. And due to its conceptual simplicity, MSD can help us to avoid the confusion, and particularly these days, a lot of research related with metamaterials and architecture materials. They often confused about the structure behavior and the material behavior, structure property and the material property. For example, this is a paper published in Science 2017. They invented a very interesting microstructure, indeed very, very innovative. When you compress it, it will twist. Okay. In that paper, they also proposed to use a 3D high-order continuum model called Kurzweil model to model this extension twist behavior. But if you read carefully, you find out this extension twist behavior will disappear or decay when you repeating this unit cell 3 dimensions, along the 3 directions many times. But only would be significant when you only have 1 direction repeating, for example, 1 or 2 directions. So if you have the unit cell repeating in the 2 directions, one of that is only keep 1 unit cell, you will have significant extension twist coupling. But from the MSD perspective, it's a plate. Okay. Then if you only have limited, a very small number of unit cell along 2 of the dimensions and repeated many times along the length direction, then you have a beam. Again, the extension twist behavior will be significant. But if you're thinking in terms of structure behavior, then that's not as surprising, because we can easily use plus minus 45 laminate to produce this extension twist behavior instead of our very sophisticated microstructures this way. So in this way, basically, MSD provide us clear thinking and also classification of what type of properties we're looking for. And MSD also have the possibility to eliminate the scale separation assumption, which they implicit the assumption for all conventional multiscale methods. We developed the heterogeneous structure elements. The basic idea is that to homogenize a block of heterogeneous system into a structure element, could be a 3D element or could be a beam element. And this element occupies the same space as the original heterogeneous element. And the result will be the effective element stiffness matrix for the element, not like a traditional multiscale method. What we do is homogenize to a point in the global model, and of course the result is the material stiffness matrix assigned to every point. And of course, this method can also be enlarged to basically, if you have a fine grid here, you have a coarse grid here, then MSD will enable you to come up with a rigorous operator to connect these 2 different grids. So somehow to add some rigorous thinking for the multi-grid method. And we also applied MSD to construct a workflow to carry out the progress damage analysis, PDA. The basic idea is to iterate over the MSD homogenization and dehomogenization process, because MSD homogenization achieves the most efficient theory for the homogenization purpose, and dehomogenization is even more efficient because it's only a matrix multiplication. So we have shown that the MSD-based PDA, the PDA can be much more efficient than the conventional approach when we do the progress damage analysis of composite structures. So as far as physics-based modeling is concerned, we believe we found the MSD to be the most suitable method for aerospace structures. It can bridge the gap between the materials and structures, directly link that, and you as an analyst or modeler to decide where you want to start, where do you want to end. And also it has possibility to remove the invalid scale separation and also assumptions within the scales. And we still use the traditional engineering models like KM single beam model or rational Mindlin model, but it has the potential to achieve the direct numerical simulation accuracy as long as it looks like a beam or like a plate. And also it has the capability to power. You can keep your structure design tool still the same, but now with MSD, you can tap into the advancements enabled by the new materials, because we will provide the accurate constitutive model for anisotropic and heterogeneous materials and structures, which is the feature of most of the advanced materials. And the last point is very important, It unifies structure mechanics and micromechanics. If you're in our field, you know there are many series, there are different series for different structures and different microstructures. And now you use MSD, the rest of that is just a simple derivation. According to Jacob Bronowski, that the progress of science is the discovery at each step a new order which gives unity to what had long seemed unlike. We know Faraday he clicked close link between electricity and magnetism. Maxwell linked both with light, and Einstein linked time with space and mass with energy. And the MSG provide a link between structure mechanics and micromechanics. Now, structure modeling can be interpreted as a special application of micromechanics. And that way here, I only provide a very conceptual introduction of MSD as a new paradigm for physics-based modeling of aerospace structures. And all the theoretical details are explained in my book to be published by Wiley before the end of this year. So, if you're interested, of course, look into the book. Also, you can email me, we can chat more. Although with MSD that we have the possibility to construct the physics-based model, there's still a few fundamental challenges that persist. Basically, all the physics-based modeling. The first challenge, what we saw is the compute bottom block, is the speed problem. For simple linear analysis, lower dimensions like 1D, 2D is pretty fast. But when you do 3D analysis, they are nonlinear. You need to do PDE, you need to do design optimization, you need to do uncertainty quantification. That becomes expensive. And also the second part is so you always need a faster model or faster code. And the second part is the knowledge bottleneck. Is that we don't have all the information, we don't have all the knowledge. Although we already get rid of a lot of assumptions using MSD, but there's still some model assumptions exist in our physics-based modeling. For example, we often work with oversimplified microstructure, and also we assume the full knowledge of the constitutive material properties, like interfaces, like failure mechanisms, which are rarely available in practice. The third challenge is that we usually need multiple models and tools to connect together to form a workflow. That's what the ICME and digital twin is doing. And if models developed by different people or provided by different vendors, then integrate those models and also maintain this integrated workflow is not trivial. And the last challenge we identified is that the accessibility, the advanced simulation techniques has been well established in academia, but the industry is lagging much behind adopting these technologies. And one of the reasons, of course, is deep learning curve, and also to get reliable results, you need highly specialized expertise. If we can democratize the access of these tools, so that anybody who can speak the engineering language can run the simulation, get the results, that would be great, because usually the normal factory floor engineers, they need the answers the most. Okay, and these challenges cannot be addressed by physics alone. This is where the AI can help. And first, we can create ultra-efficient circuit models, which prove to be very highly accurate. And I think at this point, there is no doubt that the artificial neural networks, if you have enough data, it can generate maybe the most powerful circuit models. And second is that we can leverage what is observable to discover the unknown physics, unknown knowledge, or the incomplete data, which need as inputs to our model. That is also become possible. And you just need to basically create a hybrid approach like what we did, and have the physics-based modeling and also machine learning framework to talk to each other. I will have some example to show that. And the second is that the third and fourth challenge, I think, with the recent emergence of large language model, we have a possibility. And we can create agentic AI, and with all the knowledge encapsulated, including the simulation tool encapsulated in an agent, then the humans can easily, orchestrate the workflow using natural language at a high level instead of we have to study the theory and the manual to make sure that the data transfer in a correct way. And also the large language model can significantly democratize the use of simulation tools. Now you almost have just near zero learning curve as long as you have basic engineering training, you know your question, you ask question, and large language models has the possibility to find the right tools to carry out simulation for you. And the first example here is that I will walk through some examples to demonstrate how we use AI and machine learning to address some of the challenges. The first one is really to address the circuit modeling and to speed up the process. It's a woven composites. We try to predict the thermal conductivity. For a physics-based model, what you need to do is that to first analyze at the micro scale, take the Young geometry and the fiber property, matrix property to get the Young properties, then take that as inputs to generate the three-dimensional mesoscale woven fabric finite element models and to calculate the effective properties for the woven fabric. And what we did here is that we developed a deep learning artificial neural network and include both microscale and mesoscale features, and also mix the continuous and discontinuous inputs. And we found out the physics-based simulation, including model creation and all that meshing, and it takes more than 1 hour. But the machine learning model can once it's trained, and it can be run within a fraction of a second. And also, if you're comparing the results, they almost reproduce the physics-based simulation. So that is really a game changer for iterative design optimization and other application like uncertainty quantification, which requires many repetitive runs of the model. And the second example is we address the challenge of the unknown physics. In our composite laminates, when we do the damage and failure analysis, we usually assume the failure criterion for the material and also how the material degrades once it meets the failure criterion. And here we, instead of take that assumption, we abandon that assumption and replace with a set of neural networks to be trained by the data we measured at the laminate level. So this basically, first, it helps us to discover these highly damageable material stress strain curves using the data we can measure. That's the first, get rid of the assumptions for the unknown physics, what we talking about, the knowledge bottleneck. And secondly, that it also address the challenge of limited experimental data. We don't have to rely on coupon test data like ASTM standards. We can take the surface measurements on the top or on the bottom of the laminate at the structure level and use that to do the inverse problem to find the constitutive problems. And this basically kind of like, we bring the neural networks, part of the machine learning knowledge as an approximation method to our part of our equation in our physics. And this, provide a way for us to discover unknown physics and using easy to measure experimental data. And of course, we also tried many other methods like CNNs, multi-step CNNs, and also mixed fidelity transform learning. So if you're interested, we can send you more papers in that regard. As we say that the third and fourth challenge is the code integration and also the accessibility of the simulation code can be solved or addressed by large language model. That's very recent work. We developed the composite AI as an AI-powered composite expert system to consolidate and deliver expert knowledge, including simulation tools, which is this part. And that can be enabled by API and also function calling. And if your large language model is trained and instructed to look for the corresponding simulation tools, it can be used to deliver answers. And I will have a few examples to show how we can use these models, composite AI, to run the simulation and also to integrate the simulation tools. And the first example is to run the simulation based on the machine learning models. And we know even right now there may be dozens of machine learning models is trained in the world, and also many are published. But usually we stop here. We publish a model, we show it work, then it's there. And how about we just dump the whatever you train the model into the AI system and make it work to deliver answers to others? That's basically what we did. We take the model trained about 5 years ago by Professor Liu, and after they published the paper, then the scripts are just sit there connecting dots. I say, how about you send the script to us, and we dump into composite AI. We find out that now you can use it to provide answers. And not only that, AI can automatically, based on your question, can automatically do parametric studies and also optimization. Let me see what I can fire up here to show you how it works here. So if you look at here, so I want to find the model already included. It's basically a model to predict thermal conductivity in terms of the microscale and mesoscale features. And I say I want to find effects of fiber reinforced composites, the volume fraction on the thermal conductivity of a woven composites. Can you help me? Then AI will tell you that yes, I can help you. And usually, what the trend should be, the AI already have we already trained the AI have the knowledge. And then I ask that, do you have a tool? I'm suspicious. Do you have a tool to carry out simulation to support your claim or your conclusions? Yes, they say, I have a tool. Can you provide me some data? Is the inputs, they also specify what kind of inputs they want. And or you can say just proceed with default values. I say proceed with default values. Then AI basically will take the default values and carry out the simulation and do that. And also mention that, if you want to study the effects, I can run a series of simulations for other values. I say, yes, run a series simulation for other values. Then you carry out the 3 other simulations, and AI know that they also take the default value and to make a table for me to observe the difference of the thermal conductivities with respect to fiber volume fractions. Then I will say, can you run optimization? I want to find the minimal in-plane thermal conductivity and maximal out-of-plane thermal conductivities. Yes, AI can do that, run a series one, do a design of experiment, and then say that's the minimum, or I will find that maximum will happen, even tell us that you have a 2 conflicting objective. You may want to do more sophisticated optimization that way. Okay, the second example is a real story. I have a very senior colleague, the name I will leave unmentioned. He was trained before finite element. So sometimes if we have a problem require finite element simulation, he will stop my office. So this one is basically he want to know the longitudinal and transverse shear modulus of unidirectional fiber reinforced composite. And of course, that I will do it for him. I open my model and create a finite element mesh and run the simulation and extract the results, send to him. They find out that these numbers are not realistic. Can try different inputs. I will do that. So I will repeat this process, do it again. Now with composite AI, it does not need me as a middleman to wait for my availability, have time to run the final simulations, and also do it back and forth. They can directly go to composite AI to ask this kind of questions. For example, that let me see here. You hope that the screen share there. I cannot see at your end. So I want to predict the longitudinal transfer shear modulus of a unidirectional fiber reinforced composite. Can you help me? They say, yes, I can help you. I need this kind of inputs. Then they would like to use default values or provide your own. So I provide my own. That's the first iteration I gave to my senior colleague, say fiber property, matrix property, and also hexagonal microstructure and the volume fractions. Then it will basically run the simulation, give me the results. That's basically the results I I mean, it's same as what I did the conventional way to open the code and to do it myself and send to my senior colleague. Then this man actually is exactly from his email. He said, your number is a bit high. Try different E and Poisson's ratio and all that. And AI will take it and say, oh, yeah, you didn't tell me what kind of matrix you should use. Okay, they say, do you want to still run the same matrix? Okay, yeah, it's the same matrix. Then it will give, updated number, and my senior colleague is satisfied, say, yeah, that's number are more realistic and agrees with what he expects. And so you will find out that basically I create a tool to replace myself. Do you think it's a good thing or bad thing? I think it's a good thing because my time can be better spent than just run finite element simulation, prepare the inputs and call the code and extract the outputs. My time can be better spent to create more physics-based models and add new capability to the tools. And and also it's better for the person. He does not have to wait for me. He can do many more iterations and also different scenarios. And so that not necessarily bad. It just push us to rethink what we should do in the age of AI. And the next one is basically we can integrate various tools into a workflow. And for woven fabric, I already described the usual workflow for you that we first take the yarn microstructure and fiber matrix property to get the yarn property. After we get the yarn property, we put we take it as input for the woven generator to depends on the woven patterns, and then do calculation for the effective of the woven fabric. So that's usually how we do. And we have two tools. One tool is that we can calculate any unidirectional fiber reinforced composites for any microstructure. Another tool is to generate the textile composite compute the property. And then we don't have to integrate this tool manually. We can basically use natural language to integrate the tools. And you will see here, and that is what we did. So first I will get the yarn property. Then I will say take that as a yarn property and calculate the effective of textile composite with inputs for the textile composite. It will call another tool to calculate the textile composite property. So now I say, can you integrate the above two steps to do a workflow? Now I have inputs for the microscale and also inputs for the mesoscale. I want the end results. I don't want to do step by step. And because the numbers I provide exactly the same as the previous step-by-step simulations, then composite AI know how to be lazy. They just list the results. That's what you're supposed to do. So I want to force AI to work for me, say, hey, use the workflow, but I have different numbers. So I have different woven pattern and woven composites, the geometry and also properties, and also fiber property, matrix property, even volume fraction is different. Now AI know actually integrate these two tools to transfer data between two tools and still report the results in a professional way. So you will see some of the ICME and digital twin effort can be replaced by AI. Okay, so let me close my talk with this slide. And my point is that physics-based modeling is still essential. We cannot just throw away centuries of scientific progress and hope AI alone will do all our jobs, solve every problem. As far as aerospace structure modeling is concerned, we believe that we find a good method to construct high-quality physics-based models, which can rigorously model advanced structures with anisotropy and heterogeneity, and also can provide, if you have a high-quality physics-based model, that can be used as the most efficient and robust model you could have, and also can use to provide data for AI and also simulation tools for AI to use. Besides high-quality physics-based modeling, we should also embrace AI as our helper, as a new tool to reduce computational costs, to learn unknown physics, and also to democratize the simulation tools so that engineers don't have to have deep expertise in the modeling simulation, still get reliable results, and also integrate the necessary codes into a complete workflow. And here I only highlight the AI applications in aerospace structure modeling from aerospace structure modeling perspective. If you attended my workshop, I think last Monday, you will see I demonstrated 13 applications for general engineers and can use the AI to do. And there are many other AI applications to be explored. And so I'm positive, and it's not a hype, and it's here to stay. And I will stop here and leave more time for your questions. And thank you very much for your attention.
Thank you, Professor Yu, for the presentation. Thank you very much. Let's open it for questions. We're going to do the following. We've got one or two questions in the chat. I'll ask that right now. But then, if people want to raise their hands, and we can just take the questions in that order rather than type them up. The first question here: can physics-informed neural networks be used in these kinds of case studies?
Can you say it again?
Can physics-informed neural networks be used in these case studies?
Oh, yes, of course. That you can do a purely circuit models. Also, you can bring physics to basically improve the circuit model training a little bit. And that's the one way. It's also aligned with my philosophy. We don't throw physics a lot away, but we do have to make sure that physics is physics. A lot of human-made assumptions not necessarily better than data-driven models.
Please. I have a question here from Ramulu. Please come off mute.
Yeah, he just answered. Thank you very much.
Okay, very good. All right, thank you. All right. Let's see a question. Can you provide some of the most common AI models that are being used currently or having potential for nonlinear FEM simulations?
Oh, that's a very good question. And I don't think I have, enough knowledge to say that, because, these days when you go to the conference, you'll find out most of the talks are around the AI. There are all kinds of different models. And there are some models looks like CNN can deal with some nonlinear and problems, and there are some method like a neural operator, and that's also there's possibility there. And there are some professors focusing on doing that. I'm really not deep enough to provide, say, this is the method you should go for the nonlinear or for the dimension modeling. Look at the literature. What the problem right now is that people doing this kind of research, they choose a method. They not necessarily, rigorous justify why they choose the method, and also let alone to really validate why this method is better than another method. That's, I want to say, more of the community should do that. There are so many methods, so many different types of neural networks out there. We need to bring them into a comparison, have a common set of data, like, when you look at the computer science people, how they are doing like the image recognition, right? They have a common database. Then really comparing to the orange to orange and apple to apple in terms of the accuracy and efficiency and robustness. I think we need to do more of that so that we can really pinpoint which method is better than nonlinear, which method is better than, singularity related problems, which method is better than get some of the correct uncertainty and statistics of that.
Another question is, can composites AI help us in the selection of certain damage models?
Yeah, if you put, AI, as I said, AI really, that when I teach the class, I always tell students, you cannot expect computers can do something you don't know how to do it. It's not you personally as a human. So if we instruct the AI and provide sufficient knowledge, then it can help us to do the selection. But AI fundamentally is still a model, even a statistical probabilistic model. And we know that for any model, garbage in, garbage out, if you have quality information, AI can digest it and provide you answers. If you don't have good information, then you will get it wrong. I think we have a very interesting example. And some of you, if you follow me on the LinkedIn, right, we had this American Society for Composite conference. We try to trace back the history of this ASC society. And we, asked one of the pioneers, the first president of ASC, and in composite AI gave us an answer, but the date, the ASC, the starting date wrong, 15 years different. We don't know what's wrong there, after that was a talk given in the banquet. Then going back to my hotel room, I tried to find out, trace down where the error come from. It's come from a paper on, on the top journal of our field, composite science and technology, written by the most known expert who was helping starting the society. He wrote that in the paper. That's where it comes from. So we really need to make sure the data we put in is expert certified, not just like ChatGPT you train on Wikipedia. A lot of misconceptions available, exist on the internet. We do need expert certified knowledge to get into the system. That's also why composite AI is different from ChatGPT and other systems. We integrate a layer of experts to certify the knowledge, get into the system, and also validate the response from the system and correct it. So now if you ask, when ASC was started or who is Jim Whitney, that was the initial start of our society, then it will give you a correct answer because I correct that source of error as an expert.
I think you really just answered the next question, but I'll ask it anyway. And maybe you can elaborate some more if you want to on this idea of curating the data. But the question was, how reliable is the answer of composites AI? Is it just guessing based on the data set it's trained with? And perhaps you can talk to that, to your idea of the quality of the data going in.
Yeah, at this moment, what we put is, it's mainly my papers and my book, and also Dr. Byron Pepys also have a book there. Then the simulation tools. So it's really not just guessing from the data. It's really basically, once we upload our documents, the system know how to, vectorize it intelligently, kind of like chunk it, and then basically when the large language model, the AI receives the question from user, it will go to the documents to retrieve the relevant information. Then basically it will summarize what they basically searched around the database and do the generation. That's called the retrieval augmented generation. That's for static knowledge. But for the dynamic knowledge, what called simulation tools could be physics-based or machine learning based. And those basically is what the AI's role is, mainly just interpret the intention of the user. Say, yeah, they want to carry out the simulation based on the information in that question. We say maybe this tool is the right tool for deliver the answer. Then ask the user to provide the inputs, the basic information to carry out the simulation. Then AI will call that tool as API, as if you execute the code on your own computer. So the engineering precision and accuracy is guaranteed that way. Only difference will be whether AI know how to get the right tool or not. That needs some instruction. And when you connect the tool to the AI, there's an interface to instruct you to do that. And and of course that if you look at the composite AI system, we also provide the input that AI basically takes the information from the user, generate the input file for you, and that input file also available for you to double check, to validate that the AI did a good job to create the input file. Then the code is still the executable on the side of the server. It's not guessing from random data.
I think with that, we'll go ahead and close. I think there are other comments around, the roles of SMEs, checking AI, and so on. But I think we're at the hour, so I'll turn the time back to Professor Xi, and thank everyone for their interest. And I believe there will be other opportunities to continue to ask questions and interact. Thank you.
Okay, thank you, Jonathan. Wenbing, thank you so much for a very nice talk and sharing with us your insights and your vision on how AI could advance understanding of structures with focus on physics-based modeling and also the exciting research that we could all work on. So thank you so much, Wenbing. Jonathan, I also thank you for introducing Wenbing and moderating this Q&A. For the attendees, Wenbing's talk, as noted by, Wenbing's talk is recorded and will be archived. All who register will have access to the archived version. And anyone watching the archived version in the next 48 hours could still ask questions via text, and Wenbing will reply.
Okay.
Our next AIA seminar is an author seminar to be held on November the 6th, 2025. And it will be given by Professor Dave Peters of Washington University in St. Louis and Dr. Robert Ormiston of the U.S. Army DEFCON Aviation and Missile Center. That author seminar is entitled Application of Gauss's Principles to the Classical Airfoil Problem. And it's based on paper published in the AIA Journal. So I hope you'll join us on that seminar. So once again, Wenbing, thank you so much for a very, very nice talk. And Jonathan, thank you for introducing Wenbing and moderating his talk. And also for all the attendees, thank you so much for being a part of this keynote. So wish everyone a wonderful day. Thank you so much. Bye.
Thank you.
Thank you. Thank you all for your attention. And we can continue the discussion online.
Okay, thank you so much, Wenbing. Thank you. Great
Yeah,
talk.
thank you. Thank you, Tom. Thank you, Jonathan.